Slamming a mechanical piston into a liquid should make a cooling problem harder. Squeezing a fluid under intense physical pressure is supposed to generate heat. Yet, researchers testing a pressurized salt solution measured an immediate temperature drop of nearly 30 Kelvin. The plunge happened in about 20 seconds. This method abandons the concept of an expanding gas. It relies instead on the pressure-controlled process of dissolving and precipitating a salt inside a liquid. Most cooling systems operate on the vapor compression cycle. You compress a gas, dump the ambient heat, let the gas expand, and absorb new heat from the surroundings. That cycle consumes roughly 25 to 30% of the world's electricity, and often relies on refrigerants with high global warming potential. Decoupling the global infrastructure from energy-hungry compressors and climate-damaging working fluids remains a primary challenge for large-scale refrigeration. To escape vapor compression, scientists have spent years chasing solid-state caloric cooling. A major focus within that field involves barocaloric materials, solids that change temperature when driven by mechanical pressure. But these systems run into a rigid wall. The heat is trapped within a solid. To be useful, that heat must move across a physical boundary into a separate liquid coolant. Moving thermal energy across that interface wastes time and weakens the system's performance. This physical separation also requires additional, bulky hardware to manage the heat transfer. The Chinese Academy of Sciences team calls this the impossible triangle: the difficulty of achieving low carbon emissions, high cooling capacity, and high heat transfer efficiency all at once. Efficiently scaling alternative cooling requires eliminating the physical boundary between the active refrigerant and the liquid coolant. The breakthrough came from a mixture of ammonium thiocyanate dissolved in water, placed under carefully controlled pressure. The setup appears deceptively simple: a wet saltwater mixture that looks like a disposable cold pack rather than industrial hardware. Driven by Gibbs free energy, high disordered dissolved salt competes with an ordered precipitated lattice. Raising pressure stabilizes the precipitated state, forcing salt into a geometric lattice. Releasing pressure swings the balance back to dissolution. The salt shatters, pulling heat from surroundings to complete the transition. Pressure is the trigger. The cooling emerges when the solution returns through the dissolution pathway and absorbs thermal energy. In the lab, this transition produced a temperature drop of nearly 30 Kelvin in around 20 seconds. At higher starting temperatures, the cooling span reached 54 Kelvin. Spectroscopic measurements confirmed that this pressure-driven process is immediately responsive and stable across cycles. This reversibility is what makes the salt solution a candidate for continuous mechanical refrigeration. Because the working medium is a fluid, the refrigerant and the heat transfer medium are now the same thing. This self-circulating aqueous solution addresses the impossible triangle by allowing the active cooling material to flow directly through the plumbing. The team's cycle estimates suggest a cooling capacity of 67 joules per gram with a second-law efficiency of 77%. A lab result becomes a machine only when it can survive the rigors of manufacturing, intense high-pressure cycling, and long-term operation. One primary target for this technology is the thermal management of AI computing centers. Data centers are increasingly limited by the physics of removing heat quickly and economically from high-density hardware. The next engineering challenge is building a durable pressure cycling system that can operate reliably over time. Repeated precipitation risks pipe clogging and material degradation. A functional device must maintain control over the thermodynamic cycle without letting crystals choke the pipes. If a salt solution can effectively replace the fluorocarbon cycle, the final question is whether global industry is ready to rebuild its machines around a different physical logic.